my first question for you would be to think, what do you personally wish from AI to do for you in the next year, next 2 years, 5 years, 10 years? How would you like this whole thing, this whole enthusiasm to evolve such that your life is better, you're a happier person? And what would be the most important thing for you? And I'm asking you this because I want to tell you what is the most important thing for me. And what I would like to see, the direction in which I would like to see AI to develop, is that it becomes so smart that we do not need big data, that we do not need big computation. Yes, I know it sounds not like crazy, but I have another 15 minutes to explain. You have seen lots of talk here, NVIDIA chips becoming bigger, more RAM, more computational power. You have seen another demo of a company that demos like collection of data, lots of data that are needed to train AI and so on, right? But if we want to go really, really high, we will need something. We will need AI that can learn from small amount of data and from fairly small processing power. And I want to show you some, how to advance, probably here. No, then probably here. No, then here. Yeah. This type of intelligence, which is not artificial, it's biological, natural intelligence, needs just one example of a car. This kid can see this car, you let it play with it for a little while, and this kid can later recognize all kinds of cars. It can recognize big ones, small ones, it can recognize toy cars, it can recognize drawings of cars, it can recognize even schematic cars. Everything from one shot. That's really great intelligence. That's really something great. And when we talk about strong AI, that's the direction we have to go if we want to be strong AI. But to discuss that, I would like to first say a few words about what strong AI means, because there's a confusion about this term. There has been a change historically in the meaning of this term, and in my opinion, this change is unfortunate. So it's good to clear it up at least. Today, I think most people understand strong AI as something equivalent to AGI. So intelligence, a machine that's as intelligent as human, right? And I think this came from the writing of Ray Kurzweil. However, the term comes from one philosopher who formed it, I think, somewhere in the 60s, maybe 70s, who was a critique of the AI at the time, and who meant by that term more like AI in a way humans do it. So not the level of human, but a way humans do it, which means a way biological systems do it. So he would say, for example, that his dogs are strongly intelligent. And dogs cannot read, cannot speak, cannot understand much of language, a few words, and yet they were strong in a way. So how strongly intelligent is a dog? Just consider a problem of robotics, of walking, of recognizing patterns, of understanding the space around you, and figuring out how to, in a complex environment where there's like obstacles and things like that, figuring out how to get from this point to that point, to catch a prey, to run away from a predator. Dogs do excellent job, like way much better job than any technology we have today. So that's strong. So fundamentally, the message behind that is that not human brain, biological brains, all of the brains, all the living systems, do things somewhat differently than what we have today in our technology, so that we can learn with one trial. Now, Why is that important to know? That's because we want to avoid AI winters. AI winters occurred in history when big promises have been made. We just heard a mention of that in a previous talk, and failed, right? So many people said, okay, we'll do that, we'll do that, we'll do that. Money was poured in, not as much as today, more in research than in the business, but then didn't deliver. The biggest chunk of money that was poured was, I think, by Japanese government. At some point, they decided to build really powerful AI. They poured lots of money. I think it was a 10-year project. Didn't deliver pretty much anything of what they expected at that time, right? AI winters are bad. So my second wish for AI in the future is not to see an AI winter, right? Because it's not fun. I'm actually old enough to have experienced it personally. When the time was that if you said, I'm interested in AI, it wasn't really looked good. Didn't look good, right? So you had to say, I'm interested in the brain. That was popular then, this time. So you could always change the topic. So many people say to them, nah, now it's for real. This time it's for real. AI is not gonna go away. It's not gonna go anywhere. Well, hopefully that's the case. But I would like to mention a few causes of creating AI winter so that we understand, and can prevent them. How do we overpromise something? Because we use intuition, things work on a small scale. Like you make a little demo, a few sentences, a little chatbot that can kind of intelligently answer a few sentences, and then you think, well, it works really good in the small scale. We'll just scale it up. In next 2 years, we'll have it, or in the next 5 years, it will be at the level of human. Didn't happen. So, and perception of pattern recognition and so on, the same problem, the same kind of things. Now, what makes us believe today that this is not going to be a problem again? We have improved a lot on speed and memory, as we have just seen now, and keep improving. But our technology, our concepts are basically not fundamentally different than what we had in the 80s. Right? Actually, most of the things that we use today have been invented by 80s. Right? Now, I wanted to see whether there is really a problem and try to do it in a scientific way, in a sense of estimating the real numbers, how much resource power we need to match human intelligence. Right? And to do that, you don't calculate the number of neurons and the numbers of synapses and so on. You could do that, but that's a wrong way of doing it, because this way already makes assumptions about how the brain works, but we don't really know how the brain works. So what you have to do is look human behavior. And I'm a cognitive scientist as well, so I know how to estimate. We know this and did lots of experiments, so we can know how many different things can a human distinguish and not distinguish. So we could multiply that numbers, and I came to the number of a variety. The minimum estimate is 10 to the power of 20. And the more realistic estimate is 10 to the power of 48. That's one with 48 zeros. That's how many different things a human can distinguish without learning new stuff. Already from the learned stuff, an adult person, a kid not yet, but an adult person. Right? Now, you look back, how many different things can today's AI distinguish? 100,000 is already really powerful machinery. So there are 40 plus zeros missing in the scale. That's one point. The other point, even more stronger ones, look how AI scales in intelligence. Right? To scale an AI solution in the number of customers, that's very easy. That's not what I'm talking about. I'm talking about scaling in intelligence. Think this way. You have one solution. You spend 1 year solving things, and then it works pretty well for, I don't know, say, you recognize gestures. So it works really well for 10 gestures, or quite kind of well. But your plan is to have maybe 20 gestures in the future, or 100 gestures. That's scaling in intelligence. Now, you can actually look back in the data, look in our solutions today, and probably everyone who has played with this stuff and programmed, whoever is in machine learning here in the room already knows, has a feeling for that. How much resources do you need to distinguish two categories in images to a certain level of performance? Then how many resources you need to distinguish 10? How many resources you need to distinguish 1,000 or 10,000? And when you look at the solutions, you see that the number of RAM, processing power, and so on grows not linearly, but worse than linear, right? And that's exactly why NVIDIA is making so much money, because people need this power. That's exactly why the stock prices went up. It's exactly this problem. To reach human intelligence with this math that I've just mentioned to you, it's just not doable. We would need a computer of the size of a planet to do that. I also calculated in some place how much money we would need if we bought 1 gigabyte of RAM for €1. All the money in the world wouldn't be enough to reach this. The lower limit estimate of what a human can do as intelligent behavior with the technology that we use today, with deep learning and so on. Right? So we need to change something. Now, what does this have to do with AI winter? Well, we are all fine if we are not promising too much in the terms of scaling AI. So if you have, the direct advice to you from my analysis, if you are an entrepreneur or if you're an investor, if you have a good thing working, some solution, and you just need to scale it to many customers, no problem. If you have a good thing working, but you need to scale it to working even better, more intelligence, more documents scanned, more gestures recognized, more patterns recognized, more this, more that, that's where the problems begin. That's where the things go exponentially, with much faster than the computational power, right? Much faster than the Moore's law or something like that. That's where we have to be careful. If lots of money gets poured into prediction that in the future we'll have much more intelligent AI, this could produce not only an AI winter, but also economical crisis, right? Okay. And I think this problem of scaling is also the reason why we have business models today as they are. So you have startups that go vertical. They go for one solution. Because of this problem of variety, you cannot reach that broad intelligence. You have to narrow down into some problem. You cannot, it would be ideal if we had some platform that can scale easily, as I described at the beginning, without adding lots of resources, without adding lots of RAM and a huge training data set. But we don't have it. So you have to go vertical, and then you have horizontal is reserved for big corporations to provide the surfaces, or for the open source to provide the tools for programming, implementing solutions, right? But So I want to spend my last few minutes in telling you a little bit about how I would like to solve this problem, how I would like to avoid AI winter, and how I would like to go and walk the path towards strong intelligence, towards intelligence that can learn only from few examples and with little resources. And to do that, I would like to say that I have been working as a neuroscientist for many years, trying to figure out from the brain, what is it that the brain has that we don't have in AI? And a couple of years ago, I thought I figured it out, and I published lots of papers, like very academic, philosophical. But then I decided to turn and go into industry and learn about that world that was completely unknown world for me. I was just a nerd in a lab. Now I'm a nerd in doing something else. And try to learn more about business, about technology, about how people interpret, and also wanted to get to know lots of people who do machine learning, because I wasn't connected in this direction, right? And since I co-founded 2 startups, one going completely vertical, just making one solution with existing tools, not really interesting to talk about. It's about psychological assessment of people, and then AI telling you what people are about, how to interact with them, what kind of person, put them in the categories, right? Something we all like to do. But the other one, not going completely horizontal, but kind of oblique, developing a new technology that can learn on the basis of the steer, founded in the steer, that can learn from small data sets. And something that, like this kid, right? The kid comes to the world with lots of expertise already. It's not blank. It's not tabula rasa like your deep learning network. It actually already has a lot. And then, up to this age, when it starts playing with car, it acquires knowledge in such a way that it uses it as its expertise to learn more efficiently, to have all kinds of induction biases, if you like to know, have it in the terms of machine learning. And it's a bit of a complicated theory, which I don't have time to explain now. You can see, we can Google it, of course. There's lots of papers. But what I want to tell you in the last few minutes, I want to show you a result we got, what we were able to implement, explain you a little bit how far we got. And then finally, I want to show you a clip from an animated video where we just a couple of days ago published a video that lasts 8 minutes, and I have only 4 left. So I'll just show you 1 minute from the video, right? So what we did was a common problem in machine learning, pattern recognition. This is MNIST set, very popular set, very well known, well studied, and so on, right? You have a training data set that has 60,000 of these handwritten characters. You have test data set that has 10,000 of these written characters. And if you use these whole sets, you can train lots of good kind of algorithms to do near perfectly, like 99-point-something% correct. But what if you want to use just 3? Not everything, just 3. If you want to teach the algorithm to distinguish 7s, you use 3 examples of 7s, and distinguish them from 8s, 3 examples from 8s, and so on, right? Today, it's really hard to do it with existing technology, right? So what we did was we used this digits 0s to 6 to develop expertise of the agent. So it's kind of like, you know, what the evolution did for this kid. We did with this. And we developed an agent that was an expert for characters, and his name is Mr. Character now. But he doesn't know if I deliver it to you, he doesn't do well with any characters. He's just able to learn characters quickly. Right? So here's actually, I'll show you the results how it works. Actually, we take then 7, 8, and 9 as to train it, but we use only 3 examples. We collect them by chance, so we don't use some most representative one, just 3 by chance, 3 of those, 3 of those. Run one at the beginning, of course, it's a 0 performance if we don't train it. That's no surprise. Oops. Can I go back? Can we go 1 back? 1 click back. Thank you. Oh, that's not a good color. Do people see this line or not? No, I'll trace it with a laser. I hope I don't burn the one. Here and here, okay? So after the first epoch of learning, it means just seeing these nine pictures once, training once, just 1 round. It goes from 0 to 84. No, sorry, to 89% correct. And then with another round to 90%, and then it stays at 90. But that's a training set. It's not bad because we have only 3, but it's just a training set. So the interesting thing is actually the test. The test comes with 10,000 other digits. It's another file, if you wish, with completely different digits, right? So how does this now do with the training set, right? And here's the result. So this one is visible, right? I don't need laser. So we get, after 1 epoch, we get 79%, and then in the next one we get 1%, and that's it, right? On the test. So we could, so this performance is not impressive for MNIST. If you do it in a classical way, you get to 99%, right? But here we did not do any of the optimization, any of this stuff. We just wanted to make it work, right? We would be happy if it worked with 40%, just above chance level. But it worked just that, without that. So what does that mean now here? It means that we have an agent. I'm at 0, 0. So conclusion and the video. We have an agent that is able to learn any character. Doesn't need to be 7, 8, 9. It could be anything. You could just make it up. It will just give it 3 examples. You could probably give it just 1 example, but in that case, you have to make sure that this is really a representative example. Here we use just random examples, so 3 was good to cover it. In no time, you can run it on some small computer. You don't need super powerful. You can write it on Raspberry Pi if you want. Right? Doesn't need lots of resources. But let's now see how many different things it can do, and how much intelligence does it have. It depends how we count it. If what I show you, it has a really, it's not much. It's 3, right? But the beautiful thing about it is that it can learn any writing set. How many different writing systems can you possibly have? Infinite, more or less, right? A little less, but for our practical purposes, infinite. And you can learn any of them just right there, in front of it. And you need a few examples, and then it goes. And it does a pretty good job. So if you calculate your intelligence at that level, with this fast learning stage, then it's really huge. Then you don't have this limitation that I was talking about before. Right? Now, here's one little thing I have to admit. So I said, you don't need a lot of computational power. Well, to evolve the agent, you do need. We needed, our graphic cards got really hot to evolve it. But the great thing is you evolve it only once. You don't have to train it for each additional problem where you apply it. You could evolve it only once and sell it as a product, and people can can use it for their own purposes with small computational power. Right? And the last thing is the video.
Fractopoiesis states that adaptive mechanisms of different speeds are organized into a hierarchy. First, evolution creates genes at a painstakingly slow tempo. Then gene expression mechanisms act as slow adaptive mechanisms, which enable us to learn about the world by creating new mechanisms for fast adaptations. Next, fast adaptation mechanisms change the properties of our nerve cells within seconds. Finally, the resulting adjusted networks of nerve cells route sensory signals to muscles with the speed of lightning. Only then can behavior be created. Probably the most groundbreaking aspect of practopoietic theory is that our intelligent minds are not primarily located in the connectivity matrix of our neural networks, as it has been widely held, but instead in the elaborate knowledge stored in the fast adaptive mechanisms. The more knowledge our cells have on how to quickly adapt, the greater capability we have to adjust in novel situations, solve problems, and generally act intelligently.
That's all. The entire video is 8 minutes. It has more information, but it's just a teaser. And please go to YouTube, take a look, and increase our view count, and hopefully learn something interesting. So that's all what I had. I'm in red. Please finish your talk. I'm finishing. Thank you very much.